Hello students, now in this video let us see some next properties. So let me take the theorem. Let a, b, c be any integer and m be any positive integer. M be any positive integer. Then AC congruence to BC modulo M. If and only if A congruence to B modulo M upon the GCD of M and C modulo this term. Now let us see the proof of this. So suppose here first of all what is given to us, this part is given, we have to prove this, and again this will be value, we have to prove this, that is the thing. So suppose AC congruence to BC modulo M. Then by definition of congruence we get M divides AC minus BC. M divides AC minus BC. Now that is same as by definition of divisibility, AC minus BC is equal to M into K, for K belongs to what? Set of integer. Now let D will be the GCD of M and C. Here we have to assume this. D will be the GCD of M and C. Fine. Then if D is the GCD of M and C, what does this give? This gives M divides D and C also divides what? D. C divides D. Now, as this if this is whole, therefore, now one more thing here, from this equation AC minus BC is equal to M into K, may I write as C or A minus B, I'll call it as equation number 1 suppose, then this 1 implies, I can write this 1 implies. What does this M1 implies? C is equal to what? M into K. We can write this as such. Now as this D is the GCD, we know this is greater than 0. So it will be a non-zero positive integer. So here let us divide both sides by D. So let me get, I will get AB into C minus D is equal to M upon D into what? K. If this is the case, then what does this give? This gives this M by D will be what? The divisor of this one. So I can write M by D, M upon D, I should write it as such, I couldn't write it as a slash, M upon D divides what? This A minus B into C upon D, this one. So that is same as to say, this can be written as what? This is same as to say M by D divides only A minus B. Why does this? As we see one property that if D is the GCD of M and C, then the GCD of M by D and C by D should be what? 1. We have solved one example of this kind. This is one of the property of GCD. This GCD should be what? 1. This one, the reason for this. So here as this GCD is 1, so this will be what? The divisor of A minus B. And if this is the divisor of A minus B, by definition of congruence, what do we get? A congruence to B modulo what? M upon D. What is D? D is the GCD of M and C. So the same thing can be written as A congruence to B modulo what? M upon GCD of M and C. This one. Fine. Now This is what direct part. Now let us see the converse part of this. So conversely, I can write conversely, suppose A congruence to B modulo M upon M GCD of M and C. Fine. That is A congruence to B modulo M upon D, as D is what? The GCD of M and C. Fine. So what does this gives? M upon D divides A minus B. M upon D divides A minus B. This is by definition of GCD. Fine. Or the definition of congruence, definition of congruence, not by GCD. Now, by definition of divisibility, this is A minus B is equal to what? M upon D into what? K. For some K belongs to what? Z. This is by definition of divisibility. Now, as C is one of the integers, so let me multiply both sides by C. So, it will be AC minus BC is equal to what? M into, I can write it as M into CK upon D. This CK upon D is suppose a new integer. It can be written as M K dash, where K dash is what? CK upon D. It is what? An integer. This can be written as such. AC minus BC is equal to MK dash. That is same as to say AC. M divides, this is same as to say what? M divides what? AC minus BC. And by definition of what? Congruence, we can write it as AC congruence to BC modulo M. Modulo M. This is our required proof. What we have assumed first? AC congruence to BC modulo M. Then by definition of divisibility we have written this. Definition of congruence we have written this. Then by definition of divisibility we have written this. Here we have assumed D is the GCD of M and C. Then it is a property of GCD. Later on this equation 1 we have written as such. Now as D is what? Strictly greater than 0. So we have used it here divided by D here. So here again the definition of divisibility we have used. Now again the GCD of M upon D and C upon D will be what? 1, as D is the GCD of M and C. So again the definition of this property of divisibility gives this. Then again definition of congruence we have used, and then this part. So now in converse part we have assumed this one. Again D is what? A GCD of M and C. So here the definition of congruence we have used, then definition of divisibility we have used, just we have multiplied by C. That is again another constant, another integer. It will be another integer. So again by definition of divisibility we get this, and then by definition of congruence we get this. Fine. Now from this we observe two corollaries. So let me write the two corollaries of this. So corollaries of that. Corollary. So the first corollary is if AC congruence to BC modulo M, and if M GCD of M and C is what? 1, means they are what? Relatively prime. Then in this case what? A congruence to B modulo M. A congruence to B modulo what? M. Then second, if AC congruence to BC modulo P, where P is prime, where P is what? A prime, and P is such a prime which doesn't divide what? C. Then doesn't divide C. P doesn't divide C, means what? The GCD of P and C should be what? 1. P doesn't divide C means GCD of P and C will be 1. So it gives A congruence to B modulo what? P. just like this. Here, if M doesn't divide C, then the GCD should be, suppose we can take here 2 doesn't divide 5. So, C will be 5 and P will be what? 2 here. Such a thing we can take. Then the GCD of them will be what? 1. Their GCDs are what? 1. Now, next theorem, let me take next theorem. The next theorem, the statement is that let M1, M2 and so on up to MR be any positive integers, then A congruence to B modulo mi for all I, if and only if A congruence to B modulo L. A congruence to B modulo L, where L is what? The LCM of M1, M2, so on up to what? MR. It will be the LCM of these one. Fine. Now, let us see the proof of this. One. Now, we have to prove that A congruence to B modulo each mi, if and only if A congruence to B modulo L, where L is what? The LCM of this mi's. Fine. Or the least common multiple of these mi's. So, suppose A congruence to B modulo mi. This is for all I was from 1 to R here. From 1 to what? R. Okay. Now, if this is the case, then by definition of divisibility, mi divides what? A minus B. For all I from 1 to R. Okay. Now, what does this shows? Mi divides each A minus B. Each mi divides A minus B. So, this A minus B is common multiple of each mi. So, this gives this A minus B is a common multiple of what? M1, M2 and so on up to what? M. Of all of them. Now, if L will be the what? Least among these mi's, or the least common multiple of them, of these mi's. Then, if this is the common multiple, L be the least common multiple, then this L must divide this common multiple. Then, by definition of what? LCM. Then, by definition of LCM, what we get? This L divides A minus B. And if L divides A minus B, by definition of congruence, we get A congruence to B modulo what? L. This is our forward part. Remember here, we know the definition of LCM. Here simply the definition of LCM is A minus B is a common multiple and L is the LCM, then L must divide that common multiple. L will be the divisor of it. Then it will be the least common multiple. Otherwise it is not. Simply the definition of LCM is used. Okay. Now let us go for converse part. So conversely, let me write here. Conversely, suppose A congruence to B modulo L. Suppose this, where L is what? The LCM of M1, M2 and so on up to what? MR. L will be the LCM. Fine. So, if this is the case, we get L divides A minus B. This is by definition of congruence simply. Call it as equation number 1. Fine. Now as L is what? LCM of M1, M2 and so on up to what? Mr. If L is the LCM of them, therefore what we get? This M1 divides L, M2 divides L and so on. All Mr divides L, means each Mi divides what? L. Call it as equation number 2. Therefore, by one of the property of divisibility, look at here, M1 divides L, L divides A minus B. So M1 must divides what? A minus B. Again M2 divides L, L divides A minus B. So M2 also divides A minus B. Mr divides L, L divides A minus B. So Mr must divides what? A minus B. So by property of what? Property of divisibility. By property of divisibility, what we get here? Look at here. Which property I want to use? Let me write this Mi. Mi divides L, fine, and L divides what? A minus B. So this gives Mi divides what? A minus B for all I. This is for all I. This is the case for all I. So Mi divides A minus B for all I. That is M1 divides A minus B, M2 divides A minus B, fine, and so on up to what? Mr divides A minus B, fine. Therefore, what can we write from this one itself? We have to write commonly. This one gives A congruence to what? B modulo Mi. A congruence to B modulo Mi for all I from what? 1 to R. 1 to R. For all I from 1 to R. This is the proof of this. Simply the definition of an LCM and the property of divisibility and congruence are used here. Fine. Now let us go for the next theorem. The next theorem says that if A congruence to B modulo M, then the GCD of A and M and the GCD of B and M are same. The theorem, the statement says if A congruence to B modulo M, then GCD of A and M is same as the GCD of B and M. So let us prove this. The proof of this one, what is given that A congruence to what? B modulo M. So this gives M divides A minus B. M divides A minus B. So this gives A minus B is equal to what? M into K. K belongs to what? Set of integer. Call it as equation number 1. Let the GCD of A and M is D1. GCD of A and M is D1 and GCD of B and M is what? Suppose D2. We will assume GCD of A and M is D1 and GCD of B and M is D2. Then our claim to prove D1 equal to what? D2. Our claim to prove D1 equal to D2. This one we have to prove. Now, as GCD of A and M is what? D1 and our GCD of A and M is D1. So let me use this one itself. So what does this give? This gives D1 divides A and D1 divides M also. Fine. Now if D1 divides A, so A is equal to what? K1 D1 and M is equal to what? K2 D2, K2 D1. For this K1, K2 belongs to what? Set of integers. K1, K2 belongs to set of integers. Fine. Now, therefore, this equation 1 implies. What does this 1 gives? Look at here. A minus B is equal to M into K. Let us put up the value of A. So, A will be what? D1 K1 minus B is equal to what? D1 K2 into what? K. So, this can be written as, that is what? B is equal to D1 K1 minus D1 K2 into K. So, this is D1 in bracket K1 minus K2K. Fine. So, what does this give? B is equal to D1 into some integer. So, this gives D1 divides what? B. D1 divides B. As here we get D1 divides B, and here we have D1 divides M. D1 divides M. So, what does this say? This says D1 is what? The common divisor. D1 is the common divisor of B and M. Divisor of B and what? M. But we know what? The GCD of B and M is what? D2. But GCD of B and M is what? D2. So, this gives, or this says, D1 is a common divisor and D2 is what? The GCD. So, this common divisor must divides what? D2. Call it as equation number 2. Also, similarly, we can show D2 divides D1 here. So, also, now let me take the GCD of B and M is what? D2. So, this gives D2 divides B and what? D2 divides what? M. So, that is, this gives B is equal to D2 K3 and M is equal to what? D2 K4, where K3, K4 are what? Integers. K3, K4 are integers. Therefore, equation 1 implies. How does this 1 becomes that time? A minus D2 K3 is equal to D2 K4 K. So, this gives A is equal to D2 K4 K plus D2 K3. So, D2 will be taken common, K4K plus K3. A equal to this. So, this shows D2 divides what? A. D2 divides A here. Again, as D2 divides A and we have D2 divides what? M. So, this says D2 is common divisor. D2 is what? Common divisor. D2 is common divisor of what? A and what? M. D2 is common divisor of A and M. And if, but what can we say? D1 is what? The GCD of them. Therefore, or this says D2 divides what? D1. Call it as equation number 3. Now from 2 and 3, what we get? Both are what? GCDs. D1 divides D2, D2 divides D1. So, from 2 and 3 we get D1 equal to what? D2. D1 is what? The GCD of A and M. And D2 is what? The GCD of B and M. This is the proof here. Fine. Now, let me take two formulas and so those one we have to use in the examples. So, two formulas, let me write. Suppose the formulas are two formulas: A raised to n plus B raised to n. This can be written as a plus b into a raised to n minus 1 minus a raised to n minus 2b plus a raised to n minus 3b square plus so on up to b raised to n minus 1. This one. Again, another formula is for this one, a raised to n minus b raised to n. It is a minus b, a raised to n minus 1 plus a raised to n minus 2b plus a raised to n minus 3b square plus so on up to b raised to n minus 1. Okay. Now, let us take an example on this. If, how does these are useful to us in examples? If d divides n, then show that 2 raised to d minus 1 divides 2 raised to n minus 1. This is an example with us. So, solution of this, given that what is given to us? D divides n. So, if d divides n is equal to what? D into k, where this k is what? An integer. This k is an integer. Fine. Now, I must consider what? Dividend. This is what? A divisor. I have to show this is the dividend, then this is the divisor. Means this part is some multiple of this one. That thing we have to show. So, let us consider this 2 raised to n minus 1. So, 2 raised to n minus 1. I will consider this. Now, while I am considering this and I will use this formula here. A minus b into this. My a will be 2 and my b will be what? 1. So, here b is 1, so everywhere that power will become 1. This is 1. So here I must write 2 minus 1 first. A is 2, b is what? 1. Compare it properly. Then here what I get? Here in second bracket I get 2 raised to n minus 1. 2 raised to what? N minus 1. Plus 2 raised to n minus 2. b is what? 1. Again 2 raised to n minus 3. And so on up to b raised to n minus 1. The power of a is going on decreasing. So, at last it will become 0. Here the power of b is what? 0 in the first term. The second term having the power of b is 1. Third term having power of b is 2. So on up to it goes on increasing till b raised to n minus 1. So, b is what? 1 here. So, 1 raised to n minus 1. So, that will become 1. Fine. This is our term here. Now, this 2 minus 1 is how much? 1. So, simply this bracket is our term here. So, here equal to 2 raised to n minus 1 plus 2 raised to n minus 2 plus 2 raised to n minus 3 plus so on up to what? 1. Now, here 2 raised to n minus 1 we get this. Now, let me put the value of n. This is what? Dk. Let us put that value here on right hand side. Therefore, how does this become? This term becomes, this will become what? 2 raised to n minus 1. So, or let me write this, 2 raised to n minus 1 will become 2 raised to dk minus 1. Let us solve for this. Fine. This is same as what? 2 raised to d raised to k minus what? 1. Now here let us use the same result again. This where a is now what? 2 raised to d and b is what? 1. So this will become 2 raised to d minus 1. And in another bracket what we get? 2 raised to d raised to what? K minus 1 plus 2 raised to d raised to what? K minus 2 till what? 1 again till 1. So what does this? This is 2 raised to d minus 1. Fine. Now here we get this is 2 raised to dk minus d. this is 2 raised to dk minus d plus 2 raised to dk minus 2d plus 1 up to what? 1. This one. Fine. This is same as 2 raised to d minus 1 into, what is here? This is 2 raised to n minus d plus 2 raised to n minus 2d plus 1 up to what? 1. As such we will get. Now here these all are what? Integers. N is integer, d is integer, so 2 raised to that power is also an integer. So this is an integer. So here I will get, therefore I must get what? This bracket 2 raised to, before that I must write, since 2 raised to n minus d, 2 raised to 2n minus, n minus 2d, n minus 2d and so on are all what? Integers. As I say, we should write that, are all integers. Therefore this addition of integer is also an integer, n minus 2d, so on up to what? 1. This also an integer, belongs to z. Therefore, look at this expression. What is the left hand side is here? 2 raised to n minus 1. So here, from this part we cannot show it. Look at here. If I write n as dk, then it will be 2 raised to dk minus 1, 2 raised to dk minus 2, 2 raised to dk minus 3 as such. But we cannot take this term common. That's why I go as such. Again here I have considered a is what? 2 raised to d. Then we can easily got this one. Fine. Here k minus 1. K minus 1 is this. Fine. Now here this term is the multiple of these ones. So here this term is what? Divisor of this. And this is an integer. Here clearly we got this. So this term is divisor of this. Therefore by definition of divisibility. Therefore, by definition of divisibility, we get 2 raised to d minus 1. This divides 2 raised to n minus 1. This one. This is our proof here. Okay. Now here we will stop. We will go for next video. Thank you.